Hi everyone, today we're starting Unit 5, Kinetics. We'll start with 5.1 and 5.2, which is an introduction to rate laws. So in our discussion on equilibrium, we talked about the rate of a reaction. If we look at the concentration of products and reactants, the products should be increasing over time, while the reactants decrease over time. Of course, if we have a reaction A goes to B, for example, the concentration of B would increase over time, whereas the concentration of A would decrease. And we reach a point here when the concentrations don't change, and that's what we call equilibrium. But the rate, of course, just measures how quickly the concentration changes over time. Now, the rate of a reaction is really determined by one thing, and that's collision theory. Collision theory is essentially the concept that for a reaction to happen, elements / molecules must collide with two specific factors. The first factor is that they must collide with the correct orientation. The second factor is that they must collide with great enough energy to surpass the activation barrier. What I mean by that is if I have, we'll look at this little potential energy diagram that we've seen sometimes. Let's say this is my reaction, and I have a certain amount of activation energy. I must collide such that I have enough energy to surmount that barrier, to go over that barrier, and then go down into the products. So I need to collide at the correct orientation and with enough energy, which basically means that not all collisions are successful. Let's take this example. Let's say CO gas plus O2 gas will make CO2 gas plus O. We'll say it's just a single O for the sake of simplicity here, so I can show what this looks like in a diagram. In reality, it would be O2, and we would have to balance it out. But for the sake of simplicity, let's say this is our reaction. CO can be represented as this, where we have the carbon being the black sphere and the oxygen being the red. O2 would be this. CO2, of course, is just one black and then two red spheres, and then a single oxygen just floating on its own. Let's say we have a collision where I have my CO, and it's going to bump in to an O2 with this orientation. They bump in like that. Of course, if we look at our product, we should have an O bound to carbon, and that same carbon's bound to another O. And so this collision would essentially produce no reaction because they're not in the correct orientation. However, let's say my CO bumps into my oxygen with this orientation, where now the carbon and the oxygen are bumping into each other. And essentially what's happening here is that these two are flying towards each other. They'll bump in this orientation. When this happens, we end up with the products that we want. That's what I mean by the correct orientation. They have to collide with each other, but they have to be oriented in such a way that, in this case, the carbon reacts with the oxygen, since the two oxygens aren't going to react to form the product that we want. Now, there's a few factors that will determine whether or not a reaction goes fast or slow. And so if you want to speed up a reaction, there's a few different ways to do that. One is temperature. As you might imagine, as temperature increases, the rate increases. The hotter you get, the faster the reaction goes. The next is surface area. which we'll call just abbreviated as SA. As surface area increases, rate also increases, right? If I grind something into a powder, it's going to react a lot faster than if I have it as a block. The next is concentration, which I'll call C. As concentration increases, you might imagine, rate will also increase because there's more stuff around to react. Then the last thing is a catalyst. We've discussed this before, but it's a substance that lowers activation energy. If you have a catalyst, this will speed up a reaction. In other words, just like the other ones, rate will also increase. So all of these will speed up a reaction. Now, experimentally, rate is determined pretty simply, as you might imagine. Usually what you will do is you will look at the time the reaction is ran. In this case, this example shows the time in seconds, and then the concentration of what you're interested in. In this case, it's the reaction of C4H9Cl with water. And so we have C4H9Cl plus H2O, and that makes some sort of a product. We don't really know what that product is, but it makes some sort of a product. What we do is we look at the concentration of C4H9Cl over a certain period of time, and we keep checking it. And if you want to determine the rate, it's essentially the concentration at one step minus the step before. So if I want to figure out the rate of the reaction between 0 and 50 seconds, it's just this concentration minus that concentration. You can see here, that will get you an average rate of 1.9 times 10 to the minus 4 molar per second. So it says that essentially, within the first 50 seconds of that reaction, I react 1.5 times 10 to the minus 4 molar C4H9Cl per second. So every single second, I'm reacting that concentration of C4H9Cl. And you keep doing that across the entire reaction. And what you'll notice here is that the rate goes down over time. And we're going to be discussing this a lot more throughout the rest of the unit. But generally, as a reaction happens, as reactions proceed, rate decreases. That's a general rule for pretty much all reactions. That while tabulating the data is pretty useful, we actually prefer plotting the data so that way we can visually see what's going on. So for that same reaction we saw in the previous slide, we can get this sort of a rate chart, or essentially a plotted rate data. And there's two pieces of information that we're really interested in. One is called the instantaneous rate, and the other one is called the initial rate. The instantaneous rate is basically the slope of the curve at any time point. So you can see here in this little blue triangle, the slope right there gives you the instantaneous rate at exactly 600 seconds. We're interested in seeing that because it tells us that that particular time point in the reaction, this is how fast it's going. The other one that we're interested in is the initial rate, and that is the instantaneous rate at t equals 0 seconds or minutes or whatever it is. But at t equals 0, so at the start of the reaction. The start of the reaction is always when it's fastest, and so we're interested in seeing how fast it is at the exact start of that reaction. Now, let's look at this quick example together. We're given this reaction, 2O3 makes 3O2. We're told that the rate of disappearance of ozone, which is O3, is negative 0.0034 molar per second under a certain set of conditions. And we're asked, well, what the rate of appearance of O2 is under those exact same conditions. Now, we know that we're interested in how much O2 is made under these conditions, and we know the stoichiometric ratio. And so quite easily, you can solve this by taking the rate of, I'm going to call rate for now R, the rate of O3 disappearing, and just multiply that by the ratio, by the stoichiometric ratio. We know the rate is negative 0.0034 molar per second. We know that we have 3 moles of O2 for every 2 moles of O3 in this reaction. So if we want to find the rate of O2, the rate that it appears, all we got to do is take that rate constant and then multiply it by 3 over 2 and flip the sign, right? This is disappearance. Disappearance means that it's going away, so of course the concentration should be going down. Since this is appearance, our concentration should be going up. And so when we do this equation right here, we should get that the rate of appearance of O2 is 0.0051 molar per second, which makes sense, right? I have a higher coefficient for O2, and so my rate should be a little bit higher. Since for every 2 moles of O3, I make 3 moles of O2, so I should be getting a lot more O2. The second question here is, what is the rate of the reaction? Since this is of the entire reaction, we essentially just need to take the rate for O2 or O3 and divide by the coefficient. So we can look at it from any standpoint. We should get the same answer. We'll start with O3. We know the rate is negative 0.0034 molar per second. And we know that the stoichiometric coefficient is 2. So if I take 0.0034 and divide it by 2, I get 0.0017 molar per second. Right, and that's the rate of essentially disappearance, but since it's the entire reaction, we'll typically just keep that positive. If I look at this from the standpoint of O2, it's the same thing. 0.0051 molar per second divided by 3 gets you the exact same answer, 0.0017 molar per second. So the rate for the entire reaction should always be the same, but the rate of appearance or disappearance of a particular thing depends on the stoichiometric coefficients. Now, in an actual experiment, if we're trying to determine the rate of a reaction, what we'll normally do is we'll just change the concentration of a reactant in the reaction. That will typically change the rate of the reaction. So what we do is we keep every concentration constant, except just one. We'll change one, and then we see how the rate changes, and then we'll change each and every single reactant. And we'll do this to see how each reactant affects the rate. And so, for example, let's say I have A plus B makes C. I'll run a reaction, for example, with 0.1 molar A and 0.1 molar B, and then it will make some amount of C, and we'll test the rate. That'll be rate number 1. Then I'll double just one of them, and I'll see rate 2, and I'll see if it changes. And then I'll try the other one. And then I'll get rate 3. And then we'll compare all of those and see what the reaction is actually based on. So all this experimental data used together can write what's known as a rate law. A rate law is essentially just describes how the rate of a reaction is proportional to the concentrations of each reactant raised to a power. And I'll explain what that power is on the next slide. And so, for example, let's say we have some sort of a reaction with 2 reactants. We can write a rate law like this, and they all generally look pretty much the same. The rate of a reaction is equal to lowercase k. Lowercase k is the rate constant. Now, this is not to be confused with the equilibrium constant, which uses the same letter but uppercase. The lowercase k is the rate constant. This will be times the concentration of reactant 1 raised to some exponent times the concentration of reactant 2 raised to some exponent, and so on and so forth. Typically, you'll only have 2 reactants because the likelihood of 3 things coming together and colliding at the exact same time is nearly impossible. And so you'll typically only have 2 reactants reacting at the same exact time. But a rate law can always be in this form. It's the rate times the rate constant, which is lowercase k, times reactant 1 raised to some power, times reactant 2 raised to some power, so on and so forth. Now, the actual exponents in a rate law tell you the reaction order with respect to each reactant. So, for example, let's say I have this reaction. HNO2 plus NH3 is in equilibrium with NH4 plus and NO2 minus. We should recognize that this is just a simple acid-base reaction. So let's say I run 3 separate experiments for this reaction, 1, 2, and 3. And I monitor the concentrations of each of these, and I also look at the experimental rate of the reaction. So here we'll have concentration of HNO2 and concentration of NH3. We're just looking at how much of each of these starting materials, each of these reactants we start with. And I also will look at the rate of this reaction. Let's say in experiment 1, I use 0.1 molar of each of them. And let's say I get a rate of 0.02 molar per second, for example. In experiment 2, I double the amount of just HNO2, but I keep NH3 the same. When I do this, I see that the rate doubles. So I have 0.04 molar per second. Let's say I reverse. So I have 0.1 molar HNO2 and 0.2 molar NH3. So I'm still doubled one of them. I've just doubled the other reactant in my reaction. And I end up getting the same result. It doubles the reaction rate. Let's say I decide to also run experiment number 4, just to really validate my results. And what I do is I only use half of one of those. So I use 0.05 molar instead. I've halved the reaction compared to experiment 1, and what I find is that my reaction rate ends up being half. This kind of phenomenon says that the reaction is first order with respect to HNO2 and NH3, because doubling it will also double the reaction rate. That makes it a first order. And that is what the exponent essentially means in our rate law. So I can write a rate law. They always look the same. The rate of this reaction that I'm showing is equal to my rate constant, which is lowercase k, times the concentration of HNO2. And the power here is 1, because anytime I will double something, I will also double the rate. If I have the concentration of HNO2, I will have the rate. If I multiply it by 3, I will multiply the rate by 3. That makes it first order, so the exponent is 1. And because NH3 is also the same, I'll multiply this by the concentration of NH3, also to the first power. So that reaction order essentially tells you how changing the concentration of that reactant will change the rate of the reaction. Now, you might imagine the overall reaction order is just equal to the sum of the orders for each reactant. So in this case, for HNO2 it's 1, for NH3 it's also 1, and so the whole reaction order is 2. So the reaction is second order overall. Now I'll explain these more in the next few slides. It's second order overall, but it is first order with respect to HNO2 or NH3. So each of them contribute 1 order to the whole reaction, but the entire reaction is 2 because they each contribute 1. Now, again, one last thing I've said, lowercase k, this is the rate constant. It is unique to every reaction. It's not always the same thing. You always have to determine it experimentally. It's unique to every reaction, and it's temperature dependent. So changing the temperature will change the rate constant for a reaction. And so the rate constant we can kind of use to estimate the relative rate of a reaction. And so if a reaction has a K value, a rate constant of 10 to the 9 or higher, it's considered pretty fast. For reactions with K of lower than 10 to the 9, it's considered slow. And we often will have to solve for K with units. And for example, for a zero order reaction, this essentially means that the reaction does not depend on the concentration of reactants. The units for K is typically molar or molar per second, and a rate law is just K times the concentration of A to the 0. In other words, the concentrations of your reactants have no effect on how fast the reaction goes. For an overall first order reaction, the units for K is 1 over second, or second to the minus 1. And the rate constant is this, or the rate law is this. The rate is equal to the rate constant, K, times just the concentration of one reactant, because it's only first order, only one reactant determines it. For second order, it's typically liters over moles times seconds, or per molar per second. And this will have K times A squared if it's just one reactant reacting with itself, or as we saw before, it's K times A times B, and so on and so forth. So if you get down to N, the units for K, and you never really see anything more than third order, for example, but just in case, it's this general form. You don't need to memorize this, and the rate is K times A raised to whatever power of N is, whatever that reaction order is. And so the more things you have reacting that affect the rate of a reaction, the more you have to add into that rate law. But it always has the same form. Rate is equal to K. K will always show up times the concentration of A raised to some power of N, depending on the reaction order. Now, this method that I talked about before, where we looked at the rates of the reaction and how it changes the rate constant and the rate, is called the method of initial rates, where you essentially look at that starting rate of the reaction and you will compare them to each other to figure out reaction order. So we have this example, A plus B makes 2C. Just like the other one, right? If I have experiment 1 where they're equal, I have this initial formation of C, which is 0.015 molar per second. In the second experiment, double B, and I will double the rate, which means that it is first order with respect to B, because doubling it will also double the rate. Those are proportional to each other. If I look at reaction 3 here, I've tripled the concentration of A, but I've kept the concentration of B the same. But here we can see that the rate does not just triple, right? Because if it just tripled, it'd be 0.015 times 3, which is exactly what we did between experiment 1 and 3 here. I should get 0.045. In reality, though, when B is held constant and A is tripled, my rate increased by 9. 9 is just equal to 3 squared. And so because once I tripled the reaction rate, I essentially squared the result. That means it's second order with respect to A. And so for B, it's first order, and for A, it's second order. You might notice a trend here. For first order, if I double it, I will also just double it. It is 2 to the 1 because it's first order, and so my rate is affected by a factor of 2. In this case, I tripled the rate, but it's second order with respect to that, so I raised whatever I changed it by to the power of the order of that reactant, and my rate is affected by a factor of 9 instead. And so these are the trends that we essentially have to see with these particular rates. And so if I were to write a rate constant for this, or a rate law for this, the rate would equal lowercase k times the concentration of A squared, because it's second order, times the concentration of B. And that is my rate law. I can take this a step further and actually solve for K, because I know the concentrations of A and B, and I know the rate. So let's just take experiment 1, for example. The rate is 0.015 molar per second. And for questions like this, particularly with rate laws, it's extremely important that we have the units, because everything has to cancel out at the end of the day. And you'll see this in a second. This is going to equal lowercase k times the concentration of A, which is 1.0 molar squared. The entire thing is squared, including the molar, times 1.0 molar. I'll simplify. 0.015 molar per second is equal to lowercase k times 1.0 molar cubed. And so you can see here my units are molar cubed, moles per liter cubed. I have to do that to make sure that the units of K are proper. Especially in an FRQ, if the units of K are wrong, you will get that wrong, or at least you'll get some points taken away, because the units for K can always change, depending on the order of your reaction. Now, if I want to solve for K, all I do is divide this side by 1.0 molar cubed, and this side by 1.0 molar cubed. And I end up getting K is equal to 0.015, and now we just need to look at the units. I have molar over second divided by molar cubed. I should get molar to the minus 2 seconds to the -1. And so my rate constant for this reaction is 0.015 per molar squared per second. It's a little confusing, but that's why I say for these equations, you always need to include the units, or else you're going to get the answer wrong, because the units are determined by the particular reaction you're looking at. We'll do some more examples in class together and discuss some AP Classroom problems, but for now, that's all. Thanks, guys.